MSc and PhD from IRI, New Delhi PG School. Regarding his contributions, they are tremendous at this stage. He is involved in multidisciplinary research, teaching, training, student guidance, as well as research advisory services. Regarding this teaching, like he has guided so far 3 MSc students and also guiding 1 PhD student. And he is a member of advisory committee member. He has served as more than 100 students in different disciplines. Like that's why he's involved in multidisciplinary research. And he is also involved in development of softwares and information systems and databases in SAS, macros, R packages, so which are making significant contributions for digital agriculture. So far published in more than 120 research papers, 1 book, 8 book chapters. Am I audible or not?
Yes, ma'am.
Okay. So 8 book chapters, 1 paper in conference proceeding, 14 e-articles, 18 reference manual, 2 teaching manuals, 11 e-manuals and books, 5 project reports, and many other documents like he has published and written. And he is a recipient of prestigious IRI Merit Medal for his PhD work. He has got international travel support for young scientists also from Government of India, from DST Government of India and SERB. And he attended this in University of Costa Rica. And in 2018, they also received Dr. G.R. Seth Memorial Young Scientist Award from Indian Society of Agriculture Statistics. Also won Young Scientist Award from COBACAS, Krishi Vigyan Gaurav, for carrying out research work in Hindi from ARCC and BKAS, and number of Best Poster Awards. So he has been part of the project team which received Gold Icon in Digital India Award given by Ministry of MIT, Ministry of Electronics and Information Technology. And you will be surprised, he has served as resource person for the training program in more than 10 organizations, 10 government organizations. So with that, I would like to invite now Dr. Arpan Bhomik for delivering his lecture on principal component analysis. He will do that with the help of R software, which is again open source software. And he will demonstrate the things and also give you some exercise for doing the same. So Dr. Arpan Bhomik, please.
Madam, thank you. Thank you. Good morning to all of you. First of all, I am very much thankful to Rajni Madam, my teacher also, and Dilip, our beloved junior. So Madam, whatever we have achieved, those are all due to the guidance of teachers like you. So thank you very much. Keep your blessings on me. So now, dear participant, good mornings. Although the class was scheduled 2 days ago, but I requested Madam because the farewell function for students were going on for PG School IRI, so I could not take the class. So now, principal component analysis today. I will first before I share my let me share my screen. So is it visible, Madam?
Yes, it is visible.
Okay.
Yes, sir.
So principal component analysis is an important statistical tool. Okay, it is I will explain slowly, as Madam already informed that I will also highlight it through the use of principal component through R software, the basic thing that I will highlight, because first you need to learn the basic, then you can go on and carry on the programming and learn the other things also. So, but before directly I can reach to the R software, you should know the concept, some little concept, because otherwise you will not able to interpret whatever software will produce. Software can produce anything. Software is garbage in, garbage out. Anything you will give, it will give some output. Okay. So, but the fundamental principle behind the means the program, that should be clearly known to us so that we can interpret the results. Madam, I hope the participants are all means faculty or scientific staffs.
Participants are like PhD researchers also, but mostly
Okay.
assistant professors.
Mostly and across different disciplines.
Mainly social science,
Social science aspect.
economy,
Okay.
statistics, extension.
Okay, madam. Okay.
A few are there from biological side also.
Okay. So principal component analysis, it is a multivariate statistical technique. First, multivariate means, what is multivariate? There are two types of variation. One is variate, univariate, and another one is multivariate. Univariate means when we are dealing with one variable at a time. For example, suppose temperature. Okay, so if we are only interested in that variable, so that is univariate situation, only one variable at a time, that may have a many number of observation, 10, 15, 100, that doesn't bother us. Okay, another thing is multivariate. Multivariate means when we are dealing with more than one variate at a time. Okay, for example, temperature and relative humidity. If we are considering the effect of both temperature and relative humidity on yield, so that means we are dealing with a multivariate scenario. Then we will study the joint effect of these two variables together instead of the single variate. So that is the difference. Multivariate deals with more than one parameter or one character at a time. On the other hand, univariate deals with one character at a time. That is the difference. Now, why should we go for PCA, principal component analysis? As I told, first thing, it is a multivariate technique. So when we are dealing with multivariate thing, that is the first thing. Okay, different techniques are available. So as per the requirement of the study, we should choose the appropriate one. Now, why PCA? Because the goal of multivariate analysis is to aggregate the information contained in a large data set into small manageable nuggets. Means we are having a large data set. So whenever we will deal with multivariate analysis, what is the main purpose? We will try to aggregate all the information into smaller pieces. So that is the main purpose. Now, when we are dealing with multivariate scenario, generally it is very common that there are different variables which may be correlated with each other. Okay, for example, in case of social science extension study, so there are different parameters you can have correlated. For example, attitude, cohesiveness. Okay, so a lot of things are there, so they may be related with each other. So when we are dealing with a multivariate scenario, it is very common that the variables under study will be correlated. Many variables, not all, many variables will be correlated with each other. So what is the loss actually there? So if we are dealing with all the variate in this scenario, so it is a wastage of resources because the variables are correlated, so they will highlight the same type of information. Okay, so instead of then it will be a wastage of resources. So what we do to examine the relationships among a set of correlated variable, in that scenario, it is useful to transform the original set of variables to a new uncorrelated variables called principal component. So first two things are there. One is we are dealing with a multivariate scenario, and second one is the variables under study, or there are different variables, multivariate we are dealing. So many variables may be correlated with each other. So instead of considering all the variables together, because it will have a wastage of resources if we consider different variables which may be correlated with each other. So what we do, we try to obtain some uncorrelated variables. Those are known as principal components. But all these principal components will be obtained based on certain transformation using statistical principle. But all these principal component will be function of all the original variables. Function means, for example, in case of regression, yield is a function of suppose temperature, relative humidity, like that. So you will obtain the principal components in such a way that they will become uncorrelated, but each principal component will have all the original variable in them. So that is the purpose of principal component. By doing this, we are reducing the data structure. Why reducing? Because if you are having 10 number of variables, and if we consider all the original variables, some of them may be correlated with each other. So they will explain 100% variation, 10 original variables. But if we consider 2 to 3 principal components, they may explain 80 to 90% variation, and statistically they are enough. So instead of considering all the original variables, 10 original variables, it is better we consider 2 to 3 uncorrelated principal components, each of which are function of original variables, and they will explain around 75 to 80% variation in the data set. So in order to doing this, instead of 100%, we are getting 75 to 80%, but we are number of principal component will be less as compared to number of original variables. So in that way, we are reducing the principal means data structure. That's why it is also known as dimension reduction or data reduction technique. Now, what is principal component? As I already mentioned, principal components, the main purpose of principal component analysis is to obtain certain uncorrelated observation, certain uncorrelated variables, each of which are linear combination of the original variable. So that means if there are 10 number of original variable, all of them are explaining 100% variation, you will have 10 number of principal components, all of them will explain 100% variation, but out of the 10, 3 to 4 may explain around 80 to 90% variation. Okay, rest may explain very small amount of variation fraction. So 3 to 4 PCAs will be sufficient for us instead of considering all. So that is a data reduction technique, but each of the PCA are function of all the original variable. When I will go to the practical part, it will be very clear. Another so first thing is that PCA are uncorrelated of each other. PCA are linear function of all the original variables, and their variances are in decreasing order of importance. So that means the first principal component which we will have, that will explain the maximum variation in the data structure, followed by the second principal component, followed by the third principal component, and so on. Okay, so that means their importance will be in decreasing order of magnitude. First principal component will be the most important. So that means all the interpretation mainly based on first or second principal component, generally from practical point of view. Rest we don't generally consider, but there are variances. Second principal component will explain less variation as compared to first principal component, but it will explain more variation as compared to all other principal component, and so on. So that is the fundamental thing. Now PCA, principal component analysis, is mainly dealing with explaining the variance covariance structure of a set of variable through a few linear combination of this variable. All the first two lines are almost similar. Their main purpose of PCA is to explain the variance covariance structure of the data set by doing some linear transformation of the original variable. As I told, the first principal component will be the most important principal component. So it will explain around the maximum variation in the data, followed by the second principal component, followed by third principal component, like that. Okay. So their variances are decreasing order of magnitude, and their importance are also decreasing order of magnitude. Generally, first 1 or 2 PCAs are sufficient, but from social science point of view, as far as my practical experience is concerned, I have found that at least 4 or 5 PCA final interpretation should be done based on 4 or 5 PCA, because in social science 60 to 65% variation is enough. Okay, so more variation you will not get. 60 to 65 is enough from social science. Okay, as I told, PCA is data reduction technique. Why? Again, I will repeat, because although initially we will have as many number of PCA as the original linear variable, but while doing with the final interpretation, we will focus on only 2 to 3 PCA. So in that way, it is reduce the data structure. Now, what are the advantages and disadvantages of PCA? So principal component, first you have to remember that principal component analysis is just an intermediate step. Why intermediate step? Because based on PCA, first you do the PCA and then you will do the further analysis. So principal component analysis is more of a means to an end rather than an end itself. It is not the end. After that, you have to do many things, statistical techniques as per the requirement. But PCA is an intermediate step. Okay. So it is mainly an intermediate steps in much larger investigation by reducing the dimensionality of the problem. It just reduces the data structure and then do some intermediate steps. And then finally, based on the results of PCA, you have to do the other things also. So it is a mathematical technique which does not require user to specify the statistical model or assumption about the distribution of the original variable. If you just see the regression or testing of hypothesis, there we assume, generally we assume that population is normal. Okay. And even maximum statistical theory, we assume that population is normal. Okay. So the distribution of the variable is known, but principal component analysis is flexible in that sense that you don't require any assumption about the distribution of the original variable. So original variable may be continuous, original variable may be not normal, anything you can take as original variable. Okay, so that doesn't bother. Okay, so it may also be mentioned that principal component are artificial variables and often it is not possible to assign physical meaning to them. So that means, as we told, we are having correlated data structure, and based on that we are obtaining some uncorrelated principal components, which each of which are linear function of the original variable. So sometimes what happens, principal components are artificial created variable, they don't have meaning. So what we have to do in the final interpretation, we have to, based on the score whatever we are getting, we have to identify the most important variable, original variable. Okay, so that is the thing. Now principal component analysis is of no use if the original set of variables are uncorrelated with each other. So that is the most important thing. If you are dealing with uncorrelated variables, okay, for example, temperature and application of fertilizer, so those are like some example I have given. So there are many variables which may be uncorrelated with each other. So in your data set, if the original variables are uncorrelated, so then there is no means for carrying out principal component analysis, because principal component analysis will make the original data into uncorrelated data structure. But if your original data itself is uncorrelated, so then there is no meaning to carry out principal component analysis. Okay. So now I will not go into the mathematical things in detail, but some things you have to know. Okay, one or two things you have to know. So suppose I am having p number of original variables, p may be any number, 5, 10, anything. So there will be p number of principal components also. In case of p number of variable, there will be p number of principal. P original variable, we will have p number of PCA also. Okay, that you should remember. But what happened actually, 2 to 3 PCA are sufficient. We don't focus on p number of PCA. So you see, PCAs are generally denoted by this Z. Okay, they are function of all the original variable. You see, this is the first PCA, and this first PCA consists of all the original variable x1, x2, xp, like regression. Okay, like regression. So this coefficient we need to estimate. There are certain properties. Based on that, we need to estimate this coefficient. So this is the first PCA component. Why it is first? Because it will have the maximum eigen value. So it will explain the maximum variation in the data structure. That's why it is the first principal component, followed by second principal component, followed by third, and so on. Okay. So each principal component will be a function of all the original variable. You can see in second also, but this coefficient will be different. This one and this one will be different. A11 and A21, these things will be different, and we need to estimate it. And this first PCA and second PCA, they should be independent of each other. So that means their covariance term should be 0. Okay. So now how to obtain principal components from sample observation? Okay. So for that, first what we have to do, you know, there are, for example, like we are having name, each of us having name, surname, our native place, all that. So when we are dealing with statistics, so there are one thing that is known as vector and matrix. Okay. So suppose I am having some variable. So what we have to do? First, we have to calculate the mean. So there are n number of n, maybe any number, 5, 10, any number. So if there are n number of variable, original variable, so we have to calculate the mean vector. Mean vector means there are n observation will be there in mean and variance covariance matrix. So generally this mu is denoted as mean vector, and this capital sigma that is denoted as variance covariance matrix. So the dimension of this will be n by n. So that means n row and n column will be there. And the diagonal element will be the variances of the variable. Off diagonal elements will be the covariances of the between two variables. So you just remember this one. I will not go into the details of these things. Now, if S is the sample variance covariance matrix, because the population variance covariance is unknown. So suppose P observations are there. So P by P dimension matrix you will get. And as I told, like us, we are having name, surname, all these things. So matrix are also having eigen values and eigen vector. These things characterize any matrix. Okay. So even in principal component analysis also, you will get the results in terms of eigen values and eigen vector. So just remember, any matrix, any symmetric matrix, any matrix that will have eigen values and eigen vector. So if this S is the sample variance covariance matrix, if we are having P number of variable, so the dimension of S will be P row and P column, P by P. So it will have P number of eigen values, generally denoted by lambda 1, lambda 2, like that, P number of eigen values, and corresponding to each eigen value, it will have eigen vector E1, E2, like that, of dimension P. So that means each eigen vector will also be a dimension, will also have P entries. Okay. Just again, I will repeat, for any variance covariance matrix, the dimension, if the dimension is P, that is P number of original variables are there. So we will have P number of eigenvalues, and corresponding to each eigenvalue, you will have one eigenvector. That eigenvector also consists of P entry. Why that is important, these eigenvalues and eigenvector? Because these eigenvectors forms the basic of principal component analysis, and these eigenvalues are nothing but the variances of the principal component. Now, as I told, there are P number of original variable. So you will have P number of principal components. So you will have P number of principal components. Okay. So now the question is, what will be the first principal component? So here, if lambda 1 is the first eigenvalue, it doesn't indicate that it will be the first principal component. First principal, we have denoted lambda 1 as the highest value, highest eigenvalue, followed by lambda 2, followed by lambda p. So you just remember, these eigenvalues are in decreasing order of magnitude. So that means this first eigenvalue is the highest eigenvalue, followed by second one, followed by third one, and all should be greater than equal to 0. Okay. So then the first principal component is corresponding to this eigenvalue, highest eigenvalue. So now we have to check the eigenvector with respect to the highest eigenvalue. That will give you the first principal component. So you see, this is the first principal component. I will explain in practical in details. Don't bother about this. So here you see the coefficient are nothing but the entries of eigenvector with respect to the first eigenvalues. So similarly, we have to define all these eigenvalues and like that. Now, corresponding to the second highest eigenvalue, you will have second principal component. Corresponding to the third highest eigenvalue, you need to check the third eigenvector corresponding to the third highest eigenvalue. You will get third principal component and so on. So that's how we will obtain the principal component. During practical parts, it will be very clear. Okay. So now, as I told, principal components are artificial variable. One cannot have physical meaning on principal components. So what we do, we have to calculate principal component scores. So from this function, suppose this is the ith principal component. So if you just replace the values of x1, x2, xp, and these things are the coefficient based on ith eigenvector. Okay, so you will have some values for all the observation. That is the principal component score. So wherever values are 0.5, more than 0.5, that is the important variable. Okay, so there are different techniques available. Now PCA scores are important in drawing, as I told, these are important in identifying the original variable. Why it is important? Because principal component are artificial variable, you cannot have physical meaning on them. So based on the score, irrespective of signature, you have to consider the magnitude. Wherever magnitude is more, that means the variables are important. So that's how we do the reverse calculation based on PCA, and I try to identify salient variables out of all the possible important variables. So up to this point, any questions? Because then we will have, I have not covered all the theoretical aspects because it will be difficult for many people. So just gave you the concept. If you have any questions in between, you can ask. Otherwise, after the end also I can discuss. No problem. So shall I proceed?
Sir.
Okay. Just give me 1 minute. Now first we will deal with one hypothetical data. Okay. And then in the next part, we will deal with a real data. Okay. So although the data is not related to, not from social science, it's from other science. Okay, but social science also a lot of applications are there of principal component. So this is a hypothetical data. So following data highlights average minimum temperature. So there are 4 variables are there. One is average minimum temperature. I will give some assignment from social science aspect also to all of you. I will share that with the corresponding coordinator after the class. So there are 4 variables are there. First one is average minimum temperature. They are denoted by X1. Second one is average relative humidity, that is up at 8 hours, given by X2. Third one is average relative humidity at 14 hours, that is given by X3. And finally, total rainfall, that is given by X4, pertaining to Raipur district. Means this is not a hypothetical data. Actually, I have just taken a part of the data. So pertaining to Raipur district from 1970 to 1986 for Kharif season from 21st May to 7th October. Just a part of the data I have taken. So this is the data structure. There are 4 variables are there. Average minimum temperature, average relative humidity at 8 hours, average relative humidity at 14 hours, and total rainfall in centimeter. Okay. So now, as these are weather parameters, they are supposed to be correlated with each other. Okay. So in this scenario, what we do? First, we calculate the mean of all the variable. So you see, these are the means, and this total together, that is known as mean vector. So this is mean vector, this total 4. So dimension of mean, when we are dealing with vector and matrix, we need the dimension. So dimension of mean vector here, it is 1/4, 1 row and 4 columns. Okay. So accordingly, we calculate the standard deviation and like that. Now based on the data, variance covariance matrix has been obtained. Okay. That is, I have given the upper triangular form. It is symmetric matrix. So the lower triangular will be in the symmetric form. For example, here it will be minus 4.12. Here 1.54. Here 5.14. Then in the third, here it is 8.50, symmetric. Okay. Then 54.82. So like here 92.95. So symmetric. On the upper triangular form we have given. So that is sigma. This sigma is known as the variance covariance matrix. And the dimension is 4/4, as we are having 4 number of original variables. So 4 number of rows and 4 number of columns, as I told. Now there are 4 original variables. So you will get 4 PCA. 4 original variables are explaining 100% variation. So 4 PCs will also explain 100% variation. Okay. But we have to consider 1 or 2 in order to reduce the data structure. So now the variance covariance matrix, it is of dimension 4. So it will have 4 number of eigenvalues denoted by these lambdas, lambda 1, lambda 2, lambda 3, and lambda 4. And corresponding to each eigenvalue, you will have eigenvector. You can denote it by A or E, whatever. Okay. So this software will automatically calculate. No need to bother about that. I am just explaining how you will define PCA based on this. Okay. So here the highest eigenvalue has been written as lambda 1. It is 916.902 for this data set. Second highest eigenvalue is written as 18.375. Third highest as 7.87, and fourth one is 1.056. So that means these eigenvalues are in decreasing order of magnitude. Lambda 1 greater than equal to lambda 2 greater than equal to lambda 3 greater than equal to lambda 4, and all of them are more than 0. Okay, greater than equal to 0. Now, as I told, in a matrix, we are having name, surname like that. So for any matrix, they will have eigenvalues, and corresponding to each eigenvalue, they will have eigenvectors. So corresponding to the highest eigenvalue, the eigenvector is denoted by this. And as I also told, eigenvector will have the dimension of eigenvector here will be 4. So these are the 4 entries. This may be A11, A12, A12, then A13, and A14. Similarly, this one is A21, A22, A23, and A24, and like that. Okay, now how we define the principal component? So the first principal component is defined with respect to the highest eigenvalue by considering the eigenvector with respect to the highest eigenvalue. So you can see we define the principal component by Z, Z1, Z2, Z3, Z4. So this first principal component Z1 is corresponding to this lambda 1, okay, highest eigenvalue. And here we have to, in order to obtain the coefficient, we need to see the eigenvector corresponding to lambda 1, and we have to obtain the expression. So here you see this one 006, that is this into x1, then 0.061 into x2, then 0.103 into x3, and 0.993 into x4. So these are the coefficients. So this is my first principal component. Like regression, if you put the values of x1, x2, x3, and x4, you will get the principal component score with respect to the first principal component. Okay. Similarly, we can obtain the second principal component. Second principal component will be based on the second highest eigenvalue, that is 18.375 or lambda 2, and corresponding to that we have to consider this second eigenvector. So 0.955 into x1 minus 0.296 into x2 plus 0.011 into x3 plus 0.012 into x4. Like that, you have to obtain all these principal component, but here 1 or 2 principal component will be sufficient. So 2 things here you have to see. You can see, first of all, the principal components are in decreasing order of their importance. So that means first principal component is corresponding to the highest eigenvalue. Second principal component is corresponding to the second highest eigenvalue, and so on. That is the first thing. There will be as many number of principal component as the number of original variable. So here 4 number of original variables are there, and we are getting 4 number of principal component. But out of the 4 pieces, 1 or 2 pieces will be sufficient for us for our statistical purpose, that I will explain in the next slide. And each pieces are linear function of all the original variable. You can see in each PC there are all the variables are there, and the coefficient are nothing but the corresponding eigenvector entry. Okay, and these PCs are independent. These ZIs are independent of each other. Okay, original variables may not be independent. So these things you have to remember. So now just see the variances. As I told, eigenvalues of the matrices are the variances of the principal component. So the variance of first principal component will be the highest eigenvalue, that is this one 916. Variance of second principal component will be the second highest eigenvalue, like that. Third principal component will be the third highest eigenvalue. Fourth principal component will be the variance of fourth principal component will be the fourth highest eigenvalue. Now let us see the variance covariance matrix. Here the diagonal element will be the variances of variable. For example, variance of x1 is 17.02, variance of x2 is 7.56, variance of x3 is 15.75, and variance of x4 is 903.87. And the off diagonal elements are the covariances. So covariance between x1 and x2, that is minus 4.12. Covariance between x1 and x3, this is x1 and x3, 1.54. Like that you have to define. So just take the diagonal entry, which are the variances, the sum of the variances by the original variable. If you just add all the diagonal element, you will get 944.20. Now you just add the sum of all the, means you just sum all the eigenvalues or variances of the principal component. So you can see lambda 1 plus lambda 2 plus lambda 3 plus lambda 4, that is equal to 944.20, and these two are equal. So that means total variance explained by the all the original variables will be same as total variance explained by the principal component. So if this is 100%, so that means all the principal components are also explaining 100% variation in the data. Okay, but we don't need 100% variation. We from statistically 75 to 80% variation is sufficient. Now let us see what is the variance explained by the first principal component. So first principal component, the variance explained by first principal component is the lambda 1, that is the eigenvalue of first principal component, or variance of the first principal component divided by sum of all the variance. It is 0.97. Just multiply it 100, you will get 97%. Yes, Dr. Bharti Chaudhary, do you have any question, please? Any question, Dr. Bharti Chaudhary?
No, sir. You continue, sir.
Okay.
I think it was a noise.
Okay. So, so the variance explained by the first principal components, that is the variance of the principal component divided by total variance, and you can see it is 0.97. So that means 97% variation in the data structure is alone explained by first principal component. So there is no need to consider all other principal components. It is sufficient. So that's why instead of there are 4 variables and we are getting 4 PCs, but only one PC is here alone explaining 97% variation in the data. So that is sufficient. Okay. Now second principal component, it will be lambda 2 divided by sum. Okay, like that. Now cumulative variance explained by first and second principal component is nothing but sum of their variances, that is lambda 1 plus lambda 2 divided by total variance. So you can see first and second PC, they are explaining around 99% variation in the data. So almost all the variation is explained by first PC itself, and if you just take the cumulative variance, first and second, they are explaining 99% variation in the data. So in this data set, first PC is alone sufficient, but if you want to highlight another aspect, so first or second, that will be fine. Now the question is how many PCs we should choose. In this data set, from the variation explained part, there are different ways of determining the number of principal components. First criteria is eigenvalue. So you just remember the number of eigenvalue which is more than 1, that should be the number of principal components you should focus for further interpretation. Number of eigenvalues which are more than 1, that should be the number of principal components you should focus for further interpretation. But in this data set, as I told, I have taken only a part of the data. That's why the results are little bit different. So here there are 4 variables are there. All the eigenvalues are more than 1. But here you see the variation explained. Sometime in real life, for example, in social science, there may be 7 to 8 species whose variances are whose eigenvalues are more than 1. But it will be very much complicated in that scenario to draw valid inferences based on 7 to 8 number of species. Okay, which variables are important. Okay, so there we need to check the variation explained by first or second or third principal components also. So here first is alone explaining 97%. So we may focus on first principal component itself. Okay, so okay. And from the relative importance, how to decide which variables are most important. Now we are choosing first principal component that is explaining 97% variation. And out of this first principal component, we need to now see either you obtain all the score for the data point, otherwise you just see the expression, both are same, both will do the same interpretation. Either you calculate principal component score based by replacing the variables in the data point, or you just see the function wherever more than 0.5 is there, that is good. So we will be mainly focusing on first principal component as it is explaining 97% variation. And you see among the 4 variables, this last variable is getting the maximum weight 0.993, and rest are fewer means lesser observations. Okay, so that means these x4 is what? X4 is total rainfall in centimeter. So total rainfall in centimeter is the most important variables for this particular data set, because the weightage is more here. Okay, so total rainfall is the most important variables for this particular data set. Okay, so that is the interpretation. As I told, principal components are artificial variable. You cannot do physical interpretation on them. So you have to go for reverse transformation again based on the weightage or score. So there you see the weightage is for maximum is for x4, that is the rainfall. All other are less than 0.5. So here x4 is the most important and the most important or culprit variable, you can say. And it should be highlighted. The x4 should be highlighted for further research, because it is intermediate step. So x4 should be highlighted for further other statistical analysis. So now up to this point, after that I will deal with a real data set. But now if you have any question, you can ask me. I will stop sharing, then I will do the real data set. Any questions? Are you able to follow this, what I am saying? Okay. Okay, no
Continue,
problem.
sir. There is no
Okay,
any
there is
question.
no questions, no issue. Just 1 second.
One question, sir. How to work out eigenvalue?
How to work eigenvalues? Okay.
Yes, sir.
So there are mathematical procedure involved in eigenvalues. So don't bother about that. Software will calculate automatically the eigenvalues. Okay. So I will show you how to do that. Okay, in R also. Okay. There are mathematical formulas available. One theorem is there, Cayley-Hamilton theorem in mathematics, but don't bother about that. You don't need to follow the mathematical steps. Just simply 1 or 2 line code you have to write. They will give you the eigenvalues. Okay. So now let me discuss through R. Okay. So I will just explain first the data structure, then I will also do the practical in R. So this is the famous data set. My screen is visible, Dr. Dilip?
Yes, sir.
Okay. So this is a famous data set, that is iris flower data set. So iris flower is a very important flower for for validating different statistics. Means this particular data set is a very important data set and has been used in many studies for validation, data validation. Iris flower, there are 3 types of species involved: setosa, versicolor, and virginica. So for each species, there are 50 observations are there. I have only highlighted a part of the observation. Okay. So here there are 4 parameters are there: sepal length, sepal width, petal length, and petal width. So these are flower parameter, flower characteristics. Now we have to identify which character is most important in determining the type of the flower. Okay, whether they are means this one, what I can say, whether they are petal length is important, or sepal length is important, or petal width or sepal width, whatever is important. So that's we need to now investigate it. That need to be investigated. Okay, so I will do this in R also, don't worry, I will show you. Now, when we do this per function in R, when do the analysis, there are different functions or packages available in R, customized packages available in R, which will help you in carrying out principal component analysis. But for each package, you need to customize according to your convenience. But this PRCOM function, that is the most easy function available for getting the basic principal component analysis. Okay, for further analysis, you need to do the customized coding according to the availability of the package. But in training, as the main purpose is to highlight you the means what are the techniques available, just make you aware about that. So here this PRCOMP function in R, that is very much useful in getting basic principal component analysis results. It is sufficient for basic principal component analysis. Sometimes for other studies, different complex things we need to derive. For that, customized program you need to build. But this PRCOMP function, that is the basic function which will provide you almost all the basic details required for the principal component analysis. So once we perform this PRCOM function, there will be some outputs. Some of the important outputs are HDEV. So as the name suggests, this is the standard deviation of the projected principal components. Okay. Then HDEV is nothing but the standard deviation. Rotation is nothing but the eigenvector. It will give the eigenvector, that is the rotation. And center or scale, this terminology will, center will give the mean value of the original variable, and scale will give you the standard deviation. So these things you have to remember, otherwise you will not able to see which one. Rotation, there are, for this PRCOM function, rotation will be the name which will be used for eigenvector. Okay, so now you can, if you want, you can take the screenshot of this. I will also do this in practical R, but you can take the screenshot of all these things. I will explain. Okay, first later I will explain from here. I will also do the practical, don't worry. So here, in order to perform the basic principal component analysis, any data set you need to enter. I am sure, although our classes is, I think already it should be there, and how to enter data. There are different ways of entering the data, but this iris data is already there in the data set package. So for that, I have used library data set. Data set is a package. If it is not there, you have to install it. For that, you have to write install.packages in inverted comma dataset. But here it is there. So I have, you just uploaded the function using library dataset. Then these comments I can use and I can get the output. You can take the screenshot. I have taken the screenshot from R itself. You can take, I will do the R practical also, don't worry. Okay. Now my R console is visible. R window is visible.
Yes, sir.
Okay. So first you need to enter the data. So for that, I will show you install.package. Okay. data sets. This is not required if you are not dealing with the for demonstration purpose, as iris data is inbuilt data in this dataset package. That's why I need to install it. Otherwise, you can directly upload it. Okay, no issue. Directly upload any data from CSV file. Okay, so my system, it is already installed, so I will not write again run it because it may take time. So library dataset, library function is used to call any packages available in R, and once you write library and execute it, that means that package is available for use. So library dataset, you see, it is now executed. Now let me check the data, iris data, it is the name of the data. You see, this is the data. So there are 4 characters are there: sepal length, sepal width, petal length, and petal width, and 3 species are there: setosa. So first 50 observations are from setosa, then 50 to 100, 51 to 100 are from versicolor, and then last 50 observations are from virginica. Okay, so there are 3 species. Now we need to identify which variable is the most important variable in which is playing a critical role in separating the species. Okay, so now I don't need all the column of the data file, because the last column is the species column that I am not bothered about. So I will write because I am bothered about the most important variables. So I will write iris2 as the name of another data file. So that is nothing but iris. In third bracket, I have given comma, then 1:4. So when I have written comma after any blank value, so that means all the row of the data set of the iris will be considered. So initially, my data set iris is having 150 rows and 5 columns, but I have defined a new data set iris2, where all the rows, comma means all the rows of the data will be considered, but 1 to 4 column, that is the first 4 column will be considered. So that means iris2 will be a data set having number of rows as 150, but the number of columns are 1 to 4. Okay, so that those are the first 4 columns of the iris data. So just execute it. So you see iris2 has been executed. Let us see what is iris2. So you see, this is the iris2 data. No species column is available with us. Now this is my data which I can use. So that's how you have to prepare the data. Okay, in CSV. So that is my data which will be useful in order to identify which parameter is the most important parameter in differentiating the species. So now I have to use another, I have given another name, iris.pca as my output file name. Now I have used prcomp inbuilt function, prcomp principal component, prcomp. So that will be used for iris2 data. So I have to give the name of the data file iris2 data, center equal to true and scale equal to 2. That means you have to centralize the data. Okay, standardize the data. So because sometimes data may be measured in different units, so that's why it is required. So just execute it. Now it has been executed. Now in order to see the results, just write iris.pca again and run it. So it will give you some basic results. Further, 1 or 2 things you need to write. So you see here, it is giving you first the standard deviation of the PCA, these things. So there are 4 PCA because 4 original variables are there. Okay, sepal length, sepal width, petal length, and petal width. So there will be 4 PCAs. Okay, and among the 4 PCA, these are the Dilip, please mute. I think some noises is coming. So there are 4 PCAs. So as there are 4 original variables, so these are the standard deviation. These are not the eigenvalues. These are the standard deviation of the PCA. Okay, eigenvalues will be square of this standard deviation. And see rotation, but these are the eigenvector. Okay, this is not the eigenvalues. Eigenvalues we have to calculate. This is just the standard deviation of the PCA, and variance is nothing but the square of standard deviation. So once you square it, you will get the output. That will be the eigenvalue. Okay, but these are the eigenvectors, and this is the PC1 is written wherever it is written. These 4 coefficients are the eigenvectors corresponding to the highest eigenvalue which we will obtain, or if you just square it, you can get it. Okay, so now these are the, this PC1 is the first principal component, PC2 is the second principal component, like that. So how to obtain first principal component? The expression for first principal component will be 0.52 into sepal length minus 0.26 into sepal width plus 0.58 into petal length and plus 0.56 into petal width. Okay, so this is the expression. Again, I will tell 0.52 into sepal length, 0.26 into sepal width, 0.58 into petal length, and petal width is 0.56 into petal width. Here first PC is alone sufficient because you can see if you okay, let us calculate the eigenvalues also. So iris dot these things I have already calculated, it is not required because these things already given by the PCA. In anyway, if you want to see the standard deviation also, you can write iris dot PCA dollar standard deviation, same thing, this result will come. Okay, let us run it. So same result we got here, whatever we got with the basic iris dot PCA output. If you want to see the eigenvector separately, you can write iris dot PCA, that is the output name of the file, dollar rotation you have to write, that means the eigenvector. Just run it. So again, same thing we are getting. Okay, now if you want to calculate the mean, so for the original variable, write iris dot PCA dollar center. So these are the mean of the original variable in the data. So these together consist of mean vector. Now if you want to see the standard deviation of the original variable, you will write iris dot PCA dollar scale. Just run it. This is the standard deviation of original variable, not the PCs. For PC, this is the, these are the standard deviation. Now let us see the eigenvalues. So that is nothing but iris dot PCA dot var. I have given the name, any name you can give. That is nothing but square of the standard deviation. So iris dot PCA dollar HDEV, that is the standard deviation output. If you, and square, we have just taken this symbol and square. Just run it. It has been executed. Just see the output. Now this is the output. This is the variances of PC, or you can say the eigenvalues. So first eigenvalue or highest eigenvalue, that is the 2.91. 0.91 is the second highest eigenvalue. Third eigenvalue is 0.14 and fourth eigenvalue is 0.02. That is same as the square of the standard deviation, iris PC standard deviation. Okay, so from here we can see eigenvalues is more than 1 for only one PC. One eigenvalue is more than 1. So here only one PC is sufficient out of 4 PC. So just this PC1 is sufficient, and in this PC1 you see except sepal width, sepal length, petal length and petal width, all are more than 0.5. So that means except sepal width, sepal length, petal length and petal width, all these 3 variables, wherever more than 5 value are there with respect to PC1 in eigenvector, those are very much important in determining the species. Sepal width is not that much important. However, sepal length, petal length and petal width, all these 3 are very much important in defining the variables in species, defining the species. Now in order to see the variation explained by the PC, so I have given the name as variation.pc. That is nothing but the variances of the PC, that is iris.pca.var. This is the name of the file, output file, divided by sum of this. Just run it. So you can see I have run it. Now variation.pc, just print it. So 72.96% variation is alone explaining by the first principal component. 22.85% variation is alone explaining by the second principal component. 3.66% variation is explaining by the third principal component, and very negligible amount of variation is explaining by the fourth principal component. So that means, as I told, eigenvalue here, these are the eigenvalues. So here only one eigenvalue is more than one. So one principal component is enough. And based on the one principal component, we have calculated the important variable. That is except sepal width, all three are important. Now the cumulative portion you can go on adding. So for faster two, that is around 95.81% variation is explained by the first and second principal component. So this is how we draw the basic principal components analysis in R. If you want advanced, you need to explore it. Many packages are available and you can go on and write the program, no issue. Okay. Now a lot of applications are there. I have already published some papers in soils, in the area of soil science, in more than 4 impact factor rating journal in collaboration with others. In, for example, Journal of Environmental Management, one is there, one is also 3.9, some say pedosphere. Then environmental and environmental monitoring and assessment, that is also a good journal. That is also we have used PCA. So there are different soil parameters are there. We need to identify the most important parameters. So there we go for PCA. Similarly, in social science, lot of variables are there. For example, gender is there, income, and then for example, extension people, they used to get some score data. Okay, say adhesiveness, cohesiveness. Okay, so they are variable. You can go for PCA in order to identify which type of variables are important, and you can also then later, based on the PCA results, this eigenvector itself, the PCA function itself will serve as can be serve as an index also. Okay, so for index development also, this PCA is very much useful. So now any questions? I have explained almost all the things in PCA. Stop sharing and I will answer the question, please.
Sir, there is one question. When Z1 is a PC and again why X4 is considered as important variable? You can see the question.
Yes, okay. Actually, the question here asked is not means I think he was not able to express exactly what is the thing, but I got his point. That means when we are dealing with PC, what is the need of original variable? That I think that is the question I got. As I told, principal components are intermediate steps. They are not the final steps. Okay, and they are artificial variable. So when we are dealing with original variables, those variables are correlated. So we go for principal component. So once we convert principal components, then we only 1 or 2 principal components will be we will be selecting. Okay, so instead of 5, suppose 5, for this example 4 PCs are there. We are not selecting 4 PC, only 1 PC. So one variable sepal width is almost that is not important. Only 3 variables we have identified. So once we go for PC, then again we have to identify the most important variable based on the first or second PC, not all the PC. That's why we have to means otherwise based on only PC you cannot do the final interpretation, because PC is intermediate step. You have to do the final interpretation based on the original variable. So based on 1 or 2 PC, based on their weightage, you have to identify the most important variable. That is the thing. That's why you should again focus on original variable.
Sir, next question is, what is the difference between PCA versus factor analysis?
Yes, that is a very good question, and I was expecting this. There are many you know many doubts are there among the people that PCA and factor analysis are same. Okay, actually even in SPSS software also, if you want to do PCA, there is no separate option for PCA. You have to do the PCA from factor analysis part, but there is some basic differences. What is the basic differences? Factor analysis consider those things where some hidden aspect is there. For example, a particular student, he may be good in mathematics, he may be good in physics, he may be good in chemistry. So that means science, his intellectual aspect, that is the hidden factor we need to identify there. Similarly, a particular student may be good in art and craft. Okay, so dancing. So she may not be good in intelligence aspect, but she is good in dancing and art and craft. So they are the hidden cultural hidden factor is there. So factor analysis concerned with identifying the unobservable hidden factors in the data structure. But the procedure which we use in factor analysis, principal component is a part of that procedure. Okay, means you can use principal component analysis in factor analysis for identifying the unobservable hidden factor. So whenever we are on many psychological studies, we have to identify unobservable hidden factors. Okay, there are these 4 variables, maybe one particular group variable. These 4 variables may be another group variable, like that. So that grouping variable, hidden factor, that if you want to identify that one, we go for factor analysis. But in factor analysis, we can use principal component method. That is an approach. But principal component analysis, we don't bother about the hidden factor. We just simply identify which one variable is important and we reduce the data structure. Almost they are similar, but the main difference, statistical difference, is that factor analysis deals with hidden factor. Okay, where we can use PCA as one of the method. There are different methods are there in factor analysis. PCA is one of the method, and principal component analysis is totally means it is not dealing with hidden factors. That is the thing.
Sir, there is one more question. If weight is negative but more than 0.5.
That is yes. Actually, what happened? Actually, suppose one variable weight is 0.7. Okay, and it is so positive. So it is positively affecting the response. Okay, in that dimension. But if one variable weight is minus 0.75 for the same PC. Okay, so that is negatively impacting the response. So for example, कैसे example दूं? जैसे मान लीजिए soil में lead content, जैसे एक studies we have created, we have conducted. So they are lead, boron, all those things. So lead was coming negative. So that means lead is having negative impact on the response. Whatever response, biological, microbial observations was there. So they have studied that lead were negatively impacting the response. Whereas some other soil parameters are there, they were positively affecting. Sign doesn't doesn't bother unless sign is not that much important. Only the importance is the relation. Like in case of regression, okay, some sign means negative sign means it is negatively impacting. Okay, so sign is in that way, but magnitude is mainly important, for which the main important variable in order to identify the main. If all the magnitudes are high, for example, suppose 4 variables are there. For all the 4 variables, 3 variables, you are having positive higher magnitude for PC1 and negative higher magnitude for PC1. So that means all are important, but the variable which is having negative, that is having negative impact.
Okay, sir. Thank you. I think questions are over.
Any other questions? I think I am able to make the participants little bit, giving them little bit knowledge about the principal component. Now I think you can get the knowledge. You can go on, and that is not a issue. You can use anything. Principal component can be used anywhere. Okay, so wherever you are having many number of variables, you just try to reduce the data structure. So that there you can use principal component analysis. Okay, in chat box I think there are many majorly okay, majorly they have liked my class, so thank you for that. I have also seen some of the names, for example Dr. Tai madam. So I have attended one training program with her also in my during, I think, in economics division. So some known faces are also there in the participant list. Okay, thank you Dilip for giving me the opportunity, and thank you madam for giving me the opportunity. I tried my best to explain the PCA structure. I hope participant got the things.
Have you got some kind of practical exercise for them?
I will
some real study you were talking about?
Yes, madam. I will share that with you in mail. You can give them assignment, madam. And if I think this is Dr. Sujit Sarkar is from IRI Kalimpong.
Doctor?
Sujit Sarkar, I am able to see him.
Sujit Sarkar. You can unmute yourself, Dr. Sujit.
Sujit, are you there? Because Sujit also, if he is from Kalimpong, I am not able to see his video. He is my friend, and we have also gone for principal component analysis in social science aspect. So if he permit, I can share his data also. That's why I was asking. That is already published paper, so that is not a major issue.
Published paper, one can share, no issue. I mean, they would have benefit of relating.
Okay, madam, I will share, no problem. I will share some sample data, okay, to you through mail, and they can do the practical. No problem.
So if there are no questions and session is over, I think it was an excellent presentation. As I
thank you, madam. Thank you.
Yeah, I am receiving responses from our participants. So a difficult topic explained very clearly, because as you yourself has told that it is important to understand the concept also, like instead of using the software blindly. So you have done, I think, both the jobs. You have explained that it is possible using R, as well as how theory is related to practical, what is the significance of using PCA. So really it was a very nice lecture. I'm sure it will be useful for all the participants, be it from any discipline. So
yes, it is useful, madam, for all the participants.
Yes.
Wherever psychological studies, social studies, wherever many variables are there, related variables. So they are, in order to reduce the data structure, in order to identify important variables, we can use principal component analysis.
So in fact, you can share some of your research papers also, where extensive use of PCA is being made.
Yes,
so that they will have an idea on how to use this important technique in research papers.
Yes, I will share with you, madam. I will send mail. No problem.
Sometimes we are using it and we don't know how much component of that particular technique to keep in the paper.
Yes. Actually, what happened, madam, when we deal with physical class, we explain by hand all the things. But in virtual, it may not be, actually, it is little bit difficult.
Especially when you're writing variables and all, it's not that easy.
So,
in fact,
I will share some data set, some sample data set, two, three sample data set I will share. Accordingly, they can. I will share by today evening, madam.
No issue. So that's all, participants, for today. And in fact, we would like to thank you, Dr. Arpan, for very excellent talk and for agreeing to our request. I know it's very difficult when you are involved in so many activities, teaching, guiding, and students, and then this COVID, taking all the things online. So it is really difficult, but you managed it well. And like in spite of some problem on Friday afternoon, like you agreed for today morning itself. So thank you. And we expect the similar support in future also, because of lot of demand for this training. We are required to organize one more training in the same year. So we'll look forward for your cooperation in the similar training in future also.
Thank you, madam. Thank you.
Thank you.
And if participant requires my mail, you can share my official mail also. No issue.
Yes, sure.
I think it is already there.
You can write in the chat box itself.
Madam, I will show the. I think it is there. Just check me. One second. My slide is visible.
Yes, it is visible.
These are my mail. So for official, I expect people should send mail in official mail. Okay.
Okay, good.
I have not given my phone number purposely. If anybody requires, they can take it from Dilip or madam. Okay.
Yes. No, I think mails are enough, because you can explain your things properly in email. So if required, they can take your phone number through email also. So it is good. So thank you, Dr. Arpan.
Thank you, madam, for giving me this opportunity.
Thanks a lot. So now I think it is the end of this session, a morning session. Yeah. So
may I leave, madam?
Yes, thank you very much. You can.
Thank you.
So this is the end of this morning session. We'll meet again at 2:30. So 2:30, we will just see some kind of digital initiatives of ICAR